Hello, this is Project Group 2. My name is Linnea.
And my name is Daniel.
This is our presentation for the project in the signal processing course. Introduction. Sound is a mechanical wave motion that is created by vibrations in a medium, most commonly air. These vibrations generate pressure variations in the air, and these vibrations travel as waves from the audio source. When the audio source vibrates, altering regions of compression and refraction are created in the air, and it is the pressure changes caused by these alterations that we perceive as sound. Sound waves can have different waveforms, including sine waves, square waves, and triangular waves. These shapes influence the characteristics of sound. The frequency of sound waves is measured in hertz, and is a measurement of how many peaks of the sound wave occurs each second. Higher amplitude corresponds to louder sound. Loudness is subjective and relates to the intensity of pressure variations. Higher frequency yields higher pitches and vice versa. The human hearing range varies with age, but the typical audible range is around 20 to 20,000 Hz. A bass voice sings at around 80 Hz, while a soprano can sing at 260 Hz, meaning that it would be within this range that most human sounds can be expected. Consonant sounds, which often include higher frequency components, can extend into the higher pitched components. Sounds like S, sh, and z have higher frequency components. It is important to note that individual variations exist and the specific frequency characteristic of speech can vary between speakers and cultural context. In music, pitch is related to musical intervals and scale. Instruments like pianos or guitar exemplify this, where each key or string represents different frequencies and consequently pitches. Resonance is a crucial aspect of sound production. In musical instruments, resonance occurs when the natural frequency of the instrument matches the frequency of the vibrating source, enhancing the sound. The body of the violin acts as a resonator, amplifying the sound produced by the vibrating strings. The resonance is influenced by the shape, size, and materials of the violin. The materials used in musical instruments, as well as the technique employed by a musician, impact the acoustic properties. Our signal is a recording of a violin playing an A note with a TV on in the background. So it's an audio signal. The signal was acquired using an app for sound recording on a mobile phone. The sampling rate is 48,000 Hz, recorded over a 10-second period. The smartphone doesn't add any filters, however, it uses variable bitrate, which is a compression technique used to dynamically adjust the bitrate based on the complexity of the content, so it does not directly involve signal filtering. Our signal was originally recorded on an iPhone 12 and saved as an MP3 file. MP3 uses lousy compression, discarding some audio data to reduce file size. It achieves higher compression ratios while maintaining audio quality. MP3 supports variable bitrate encoding, allowing higher bit rates for complex audio passages and lower bit rates for simpler sections. While MP3 achieves significant compression, it involves a trade-off with some loss of audio information, particularly at lower byte rates. Higher byte rates, however, offer better audio fidelity. MP3 is universally supported across various devices and platforms, making it one of the most compatible audio formats, which is relevant in our project since we need to export the files across devices and into MATLAB so that we can filter it. We later discovered that it is possible to change the settings on the phone so that the file was saved as an M4A file. And because it is recorded on an iPhone, it supports Apple Lossless Audio Codec, which is a type of lossless compression like MP3. M4A supports variable bitrate encoding. It is known for preserving more audio detail at lower byte rates compared to MP3. M4A is well supported within the Apple ecosystem, but may require additional software or conversion for broader compatibility outside Apple devices, which we thought might not be ideal for our project, but turned out this lossless compression option preserved more audio detail while still being compatible with MATLAB, aligning with our goal of accurate signal filtration.
As said before, our signal is a record of a violin playing an A note with the TV on in the background. The sampling rate is 48 kHz recorded over a 10-second period. Now we expect the signal to be composed of the harmonic frequencies of an A note, that being, as you can see here on screen, 27.5 times 2 to the power of k being uh, a positive integer. So, for example, 440 Hz and 880 Hz, which you can very prominently see on the screen here. We also expect to get noise at the frequencies of human speech. In the frequency domain, prominent peaks are evident, corresponding to the resonant frequencies of the violin, as you can see on here and here, being the 440 and 880. Notably, there is a distinct large peak at 1323 here, which is not an A note, notably. And during the course of the project, it became identified as the mystery frequency. Its origin was initially unknown and posed a question for investigation. The smaller peaks observed can be attributed to background noise from the TV. Examining the time domain reveals amplitude inconsistencies, a consequence of the note being played by a human and not made by a computer. The variations in pressure on the bow against the strings, coupled with the nuanced movements required to introduce subtle patterns into the signal. For instance, a discernible pattern emerges wherein the amplitude gradually increases, followed by a decline, and subsequently another ascent. Descending amplitudes corresponds to the player naturally increasing pressure on the bow, influenced by gravitational force and a growing confidence in producing the correct notes. Conversely, the rapid descent in amplitude occurs when the bow changes direction, necessitating a momentary pause in play before resuming. The inconsistencies in the signal at the beginning and end is simply the playing starting and ending. From our project plan, we had the following research questions. What filters are needed to sufficiently remove the noise surrounding the violin playing, and can we reverse it and remove only the violin? But after starting the project and discussions during the project plan meeting, we changed our research questions to the following. Can we remove the talking part and have the violin left? And can we reverse it and have only the talking left? And then finally, what was this mystery frequency at 1300 Hz? In order to find the mystery frequency at 1300 Hz, we constructed a digital bandpass filter to extract that specific frequency and then listen to it. It was clearly a sound component from the violin, but was not part of any of the frequencies belonging to the A note, but rather an E note. Filtering out the A note was done in much the same way. A number of bandpass filters were constructed at all the resonant frequencies belonging to the note in question, from 27.5 Hz to 7040 Hz. This way, the note produced by the violin was isolated and could be either played by itself or be subtracted from the original recording to get only the TV sound. In all cases, we found that grade 6 Butterworth bandpass filters made with MATLAB's filter designer worked really well.
When examining the processed signals within both the time and frequency domain, notable characteristics emerge from the filtration of the recorded audio. The processed signals in the time domain reveal distinct patterns. In the case of isolating the violin's tone, the resulting waveform is much smoother once the noise from the TV was removed. The attempt to filter the TV sound was now far less affected by the turns of the bow, indicating a partial isolation. Transitioning to the frequency domain, the Fourier transform highlighted the frequency components present in the signal. For the filtered violin tone, the dominant peak aligned with the expected frequency of the A note. In contrast, the filtration of TV sound exhibited a substantial reduction in frequencies associated with the violin, yet residual peaks hinted at the challenge of complete isolation. Were the results as expected? The results generally aligned with expectations, given the complexities of isolating specific sound sources in a mixed signal. The ability to preserve the primary frequencies of the A note in the violin tone filtration was anticipated, although some residual frequencies were inevitable. The challenge in fully isolating the TV sound while reducing the impact of the violin was expected due to the overlapping frequency components. So removing the TV sound and keeping only violin. The method was relatively successful, preserving the essence of the violin's tone. The imperfections observed were consistent with the inherent challenges of filtering complex audio signals and isolating TV sound. While not perfect, the reduction In the impact of the violin demonstrated partial success. The presence of residual frequencies highlighted the intrinsicies of isolating overlapping sound sources. And lastly, identifying the mystery frequency. The unexpected frequency was successfully identified as a resonant frequency of the E note. This discovery provides valuable insight into the nuances of the violin's performance. And now we're going to play all of our signals. So we will start by playing our original signal.
And then we have the signal where we've isolated the violin. Then when we isolated the TV. And finally the mystery signal. In this project, we explored signal processing, particularly in the realm of audio signals and filtering. By recording the sound of a violin while background noise from a TV was active, we formulated 3 research questions to investigate and apply various filtering techniques. Filtering the violin's A note, the results demonstrate a relatively successful filtration in isolating the violin. Although some associated frequencies were filtered out, it is crucial to note that despite minor shortcomings, the technique managed to create a clear audio representation of the violin's tone. And when it comes to filtering the TV sound, then isolating only the TV sound proved to be a challenge. With some frequencies from the violin still audible, we speculate that to be the result of both the 2300 and 23 Hz mystery frequency and others like it. Nevertheless, the impact of the violin was reduced. This outcome indicates both successes and challenges in isolating specific sound sources in a mixed signal. Identification of the mystery frequency, the 1323 Hz signal, while working with the signal, an unexpected frequency at 1323 Hz was discovered. This frequency was identified as a resonant frequency for the E note of the violin. This phenomenon can be attributed to human factors such as tuning errors or slight imprecision during playback. It could also be noted that the A and E strings are next to each other on the violin, and so it could be that it would vibrate from its proximity to the A string, or simply that it was partially played by the bow while playing the A note on accident. For discussion of results, well, the results align with the research questions, but it is essential to acknowledge certain limitations and complexities in the filtering process. Depending on the objective of the filtration, different methods and adjustments may be necessary to enhance the quality of the results. As for reliability and future actions, well, to increase the reliability of the results, future work could involve fine-tuning filtering algorithms and utilizing advanced techniques to reduce overlapping frequencies, as well as finding and filtering more stray notes from the violin. Additionally, a more precise calibration of the violin and recording equipment could enhance the accuracy of the results. As for reflections and conclusions, the work has contributed to an increased understanding of signal processing and the filtration of audio signals. Despite some challenges, the results indicate the possibility of selectively isolating sound sources. Knowledge of the unexpected resonance frequencies also highlight the importance of considering human factors in signal analysis. In the retrospective view, there is always the opportunity to improve and refine methods based on obtained results. Thank you.